Good luck.
Right, good morning everyone. This is week 5, lecture 1 of CS50DC. Quick reminder about the hackathon. If you're interested, please sign up with Mr. Wood. Please let us know if you're coming. It's happening next Wednesday from 5 till 10. We'll just all sit together, do some coding, eat some food, and have fun. Now today we're going to be talking about some complicated stuff. And I don't expect you to remember all of this. What I mean is, I don't expect you to keep it in your memory. Memory. Computer's memory is finite. When we've been talking about the hardware of a computer, we've been talking about sticks of RAM. Now, in theory, if you had an infinite amount of memory, you could perform an infinite amount of calculations, do an infinite amount of processing with the computer. Except we don't. We have a finite amount of memory. And it's important to remember this. And in order to remember this, we often draw a memory diagram. Now, our computers these days might have 4 gigabytes of memory, 8 gigs of memory, 16 gigs. This here, let's say, is a 24-byte stick of RAM. Each of these squares represents 1 byte in our memory. And now imagine we're running a program. As we said, the programs are what store stuff in the memory when they're running. Imagine we store a character in one of these bytes. As we know, characters are a 1-byte data type. Char, when we did size of char, it returned 1. We could store the character, capital A, in that byte. And as we actually know, computers don't work with characters, they actually work with numbers. So deep down, that character A is actually a number. And even deeper down, it's not stored in decimal, it's stored in binary. But since we're humans, we don't need to think in binary. We can think in terms of the character A, because the computer is going to read it as a character. Now, characters are 1-byte data types. But most of the data types we worked with, ints we work with a lot, those are 4 bytes. So if we declare an int A, it would take 4 bytes in memory, 4 of these squares. And the compiler would label it as int A, so it can remember that these 4 bytes represent int A. Again, deeper down, it's actually binary. And even deeper down, if this clicker works, we can see that since it's 4 bytes, any of the bytes that don't have any information in them will just be filled with zeros. Because any leading zeros don't affect the number. But again, we don't need to think in terms of binary, we can think in terms of an integer, because we're humans. We don't need to worry about the bit level information. We don't need to worry about the ones and zeros. But now let's look at another data type that we've been talking about. Strings, which we've been working a little bit with. Printf, hello world, printf, %i, where you substitute in your string. Strings, fundamentally, are just sequences of characters. The string mark is just capital M, A-R-K. And that means we can store them in our memory as individual characters, and each character taking up 1 byte. So if you think about it, this string, which we've called S, which contains the word mark, is actually just 4 characters stored in sequence. So the string S consists of 4 1-byte long characters. So this string happens to be 4 bytes long. And unlike int and char, it's not a fixed length. We got to remember that, because this string could be any number of characters. If the word was Ojun, it would be 6 characters, OH space J-U-N. But in this case, we've got 4 characters stored one after the other. And this is what a string is at its core. It's a series of characters, or an array of characters stored next to each other in your memory. So let's take a look a little bit deeper into strings. Imagine we set up a program that takes a string from the user. So we'll use the CS50 library so we can have the getString function. And we will also include standard I/O so that we can actually use printf. Oops. Save that so we get the syntax highlighting in demo. And let's say in this program, all we do is ask the user for a string. String s equals get string. So that get string is going to prompt the user for a string, and then save it in the string s. We've seen stuff like this. We've done problem set 1. We've had to ask the user for input multiple times. This is nothing new. Once we get the string, let's just print it out. ampersand s for a string substitution with a new line, and print out the string s. Very simple program, hopefully should compile. So we give it a string, we've been working with Mark, let's go with Mark, and it prints out Mark. Wow, what an incredible program. But essentially we need to think back to what was happening with our memory. The string s gets the string M-A-R-K, and then that string s gets stored somewhere in memory and labeled as the string with the name s consists of these 4 characters, 4 individual bytes, M-A-R-K. 4 individual bytes, I've been saying that repeatedly because actually in a string, sometimes you might need to work with the individual characters. Imagine you're encrypting and you need to shift each of the characters by a certain number, for example. You'd need to be able to work with each individual character. And in fact, there is a way for us to do that in C. So what we can do is, instead of printing out the entire string, let's say we want to print out each character on a new line. Well, let's change that, because that's just going to print it off on one line. And let's make a for loop here. We'll start with 0 for the 0th character of the string. Got to make that int I equals 0. And we need to go until this I is the length of the string. We need, in the case of Mark, there are 4 characters. So if I starts at 0, we want it to end at 3. So we go 0, 1, 2, 3. So how do we know how long the string is? Well, it turns out there's a function in C called strlen which does that for us. It tells us, returns the integer value of the length of the string. So we'll go for I less than strlen of s. And then we'll do I++, set up this for loop. Now, here is the part where we print out the individual characters. Before, we would have substituted %s to do the entire string. But in this case, we're going to do a %c because we're printing individual characters, followed by a new line. And finally, to actually access the ith character of the string, to access either the first character or the second character, or even the 0th character, since we're counting in computer speak, we use the square brackets. So whatever number we put inside the square brackets is which index in the string it's going to print out. So let's test this out. Hopefully this should work. And it hasn't. Let's look at what's happened. Implicitly declaring library function strlen with type unsigned long blah 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 blah. And Clang has been very helpful here, and it's told me that I've forgotten to include string.h. So now, string.h looks similar to CS50 and standard.io.h because it's the exact same thing. It's a library that includes a bunch of functions that the C authors have written. In this case, this library contains a bunch of different functions that help you work with strings. For example, strlen, which actually counts the number of characters in a string. So let's now recompile /string. Hopefully we don't hit any runtime errors because we compiled the program fine, but there might be some kind of error when it's actually running. We'll go for Mark again. And there we go. It printed each of the characters of the string on a new line and then stopped. This program works, so it's correct. The correctness of this program is good. But the design might not be so good. Let's take a look a little bit deeper into this for loop and see what's actually happening. So, the string s gets a string, that's all good. Then the for loop starts. So we know that this is the initialization part of the for loop. Int I will get 0. So the value of I somewhere in memory will be the number 0. Then, it's going to check I is less than strlen of s. Strlen of s, Mark is 4 letters, Mark is M-A-R-K, 4 letters. Okay, so we want to check I is less than 4. Then we print out the string's ith character, so it's going to be 0 because I is currently 0. And then we increase I by 1. Now, I is currently 1, and we check the condition again. We check that I is less than strlen of s. Strlen of s, Mark, M-A-R-K, that's 4. Okay, so we need to check that I is less than 4. Print out that character, print out the first character, or the 1th character. Then increase I to 2. I is now 2. Check that I is less than strlen of s. S is Mark, M-A-R-K, 4. You see what I'm doing? I'm counting Mark multiple times, even though the length of Mark doesn't change. So what's the point of me, the computer, having to count the number of characters in mark each time I run this loop. What I actually need to do is count the number of characters once and store it, because the mark string is not going to change its length suddenly in between the loop. So recalculating the strlen of s each time is not helpful. It's actually wasting time. The computer's wasting time counting something it's already counted. So, interestingly enough, in the for loop syntax, the authors of C realized that sometimes you need to have two variables initialized at the beginning of the for loop. So you can actually initialize two integers. We can go for n, because n is often used for length, and we can call n strlen of s. And then instead of checking I against strlen of s, we can check I against n. Okay, that's not good. So now we can see, we still have the strlen of s, but instead of directly checking I against that each iteration of the loop, we're now going to calculate that value first, keep it stored so that the computer doesn't have to waste processing time in order to recalculate this each time. So let's take a look at what this does, whether it does anything different, and hopefully it doesn't. It worked. So we got mark, and then we printed out each of its characters on a new line. Now, if we go back to our memory diagram, let's look a little bit deeper into what's going on. As we said before, here, when we take that string s into memory, we store it in 4 characters. And of the string, this is character 0, this is character 1, this is character 2, and this is character 3. And the length of the string is 4. So when we start our for loop with I equals 0, and then we go s square brackets I, we get this character, capital M. Then we increase I to 1, we get A. I is 2, we get R. I is 3, we get K. Once I is 3 and it increases to 4, it's no longer less than 4, so the loop stops. So it doesn't try and print any other characters after it's printed 0, 1, 2, and 3. That's how the for loop in this situation works. Now let's come back to this diagram, because I've actually lied a little bit. When I said that these 4 bytes get labeled as int A, that's actually not true. The compiler only labels the first byte as int A. The reason it can do this is because it knows that integers, the data type int, is always 4 long. It's always 4 bytes long. It has a size of 4. So the compiler stores, the program stores the information that the address of A is some byte over here, and the next 3 bytes are part of it as well, because it knows that ints are always going to be 4 bytes long. For a char, that doesn't change anything, by the way, because a char is only 1 byte long, so it keeps that byte labeled, and the compiler knows that that is the only byte that corresponds with char C. Int A, on the other hand, has this byte and the next 3. So if we look at our string, we know that the program doesn't actually label multiple bytes as part of the same variable, it only labels the first byte. Well, with ints, it knew that each int is 4 bytes long. But with strings, as we talked about earlier, we could have strings with different lengths. Mark happens to be 4 bytes long, but Ojin is 6 bytes long. Murtaza is 7 bytes long. So, how does the program know where the string ends? With ints, it knows ints are always 4 bytes ahead. In this case, the string happens to be 4 bytes as well, but it wouldn't know that always, because strings could be variable lengths. And this would cause a problem, because if we then inserted a new string somewhere else in memory, and then we tried to read this string, we wouldn't know where to stop. The compiler would go to string s and then keep reading the string. So if we tried to print out string s right now, it would go M-A-R-K-O-H space J-U-N. It wouldn't know where mark actually ends and Ojin actually starts. So what we have to do is for the program to keep track of where the string ends. And it does this by adding a \0 character. That's not 2 characters, that's not backslash then 0, that's a \0 character. In ASCII, that would be 8 zeros. This character is known as null, N-U-L, and it's the string terminator in C. It tells the program where the string ends. That way, we can create a new string T and have it afterwards, and then when we're reading the string mark, M-A-R-K, null, we know to stop there and to not keep reading. So this is how we delimit strings in the actual memory of a computer. And we're going to take a look now at how this is actually used. Let's try and make strlen. Let's try and make the strlen function. Let's go for a new file, save it as strlen.c, and we'll include the same libraries as we did, except we won't include the string library because we're going to implement that function ourselves. So we'll include the CS50 library to obviously get input from the user. We will include standard IO, so we can print stuff out. We will not include the string library. We're going to create a function, which is going to return an integer. Strlen returns an integer. Let's call it lenstr, because strlen is already taken by the library function. And we pass it some kind of string. Let's go ahead and write our main program. Void. And say, do the exact same stuff we did. So string s equals getString. We're going to prompt the user for a string and save it in a variable called s. So remember, we need to call this function actually by remembering to put the parentheses there. So the difference between this and this is that this actually runs the function getString, whereas this just gives you getString, so that doesn't actually really work. You have to call the function using parentheses. Then we're going to do printf lenstr of that's not how we do it. We'll do printf, substitute in an integer, finish out with a new line, and do lenstr of our string. Now, if we save, compile, and run now, let's see what happens. We've called it strlen. Ooh, okay, this file's in the wrong place. I will just change my directory to workspace, because as we can see, the strlen file is in the workspace directory, not the demo directory. So we can go for make strlen. We have an error. Undefined reference to lenstr. So what happened? We actually defined it. We declared the function here. What we didn't do, though, is define it. We didn't actually tell the compiler what this function does. As Will showed us yesterday, when we make functions, we need to actually write the code that those functions do when you call them. So when we tried to call this function lenstr, the compiler got confused because it knew the function existed, but it didn't know how to actually run it. So let's go ahead and, first of all, give this string a name that it's passed, because when we give arguments to functions, we do have to give them names. So let's call this string str, for example. And then we can redefine this, or not redefine, we can actually define this function after we've declared it with the prototype, and call it lenstr again, because we're defining the same function. But this time, instead of having a semicolon at the end, we're going to open a block using curly braces. So anything that's inside curly braces in C is called a block. It's a block of code that runs under certain conditions, or when it's called, etc. Let's define this function. We'll say int n equals 0. So at the beginning, the length of the string is 0. Then we'll say while str n is not equal to backslash 0. Put that in parentheses. N plus plus. And then return n. Let's first confirm that this works before we go and analyze how it works. Go ahead and make strlen dot slash strlen. Let's give it Ojun. Length 6. That's correct, right? There's 6 characters in Ojun. How did we get this to work? Well, let's go back to our memory diagram. Here. If we look at the string Ojun, when we start our for loop, in the lenstr function, we have a variable n that starts at 0. And then we go to the nth character in the string, which when n is 0 is O. O is not backslash 0, so n gets increased. And then we move on to the nth character of the string. N is now 1, so we check h. H is not backslash 0, so we increase n by 1. We then move to the space. We keep going. We keep increasing n. At this point, n would be 5 when we check the n. We increase n to 6. So 6 over here is actually the 7th character in the string if we're thinking in terms of humans, but it would be number 6 because O is number 0. The 6th character does happen to be a \0, so the while loop stops and n doesn't get increased any further. So this is character number 5, the n, but n does get increased to 6 before it stops, because when it does hit the \0, it's already at 6. So that's why we get the right number of letters. We get 1, 2, 3, 4, 5, 6 letters when we call our length_stir function. So that's a little bit more about how strings are terminated and how the strlen function might work. This is why it's important to end the string, because otherwise we don't have any way of making strlen work. If we go back to this diagram, there are no \0s to tell the strlen function where the string ends. So let's rewind a little and go and look at our string.c function. One thing we've been doing, which is kind of bad practice, is assuming that getString will always give us a string. Why shouldn't we do that? Well, it turns out that when people write functions, sometimes there are error cases that might happen. Because as we talked about finite memory, we know that if we type the string ocean, our 4 gig memory is not going to run out. But if somebody went and typed the entire collection of human history books ever written into there, we might run out of memory. And in that situation, the getString function needs to tell the program that I didn't have enough memory to store this. So it returns a value called null. Not the same null that we looked at \0. That was NUL. This is NULL. So what we need to do is make sure that getString didn't return null. So we need to make sure that if s is not equal to null, and it's a special value in C, which means it's not actually a string, it's not the string NULL, it's a special value called null. So in case getString did return us null, we need to make sure we don't try and use that string, because that's going to cause some errors. So we need to check each time we use getString that the string returned wasn't null, that it is actually a string. And of course that's not going to affect the, that's the wrong program, that's not going to affect the actual program, because we are passing it normal length strings that aren't going to crash it. But it is going to make it more safe. It's less likely to crash. Because in case somebody did go ahead and write the entire human history in that string field, the program would crash if we didn't check that getString didn't return null. So that's another improvement on our program. Now it's more safe. It's more likely not to fail. So in a sense, its design has been improved even further. So that is a more complete way of using getString. And on that point, are there any questions regarding memory or strings or string termination or anything that I've talked about today? Because as I said, I did not expect you to store all of this in your memory. Any questions?
Could you tell us more about the null character?
The null character?
Yeah.
So
not the \0, the actual
Oh.
NULL.
NULL, right. NULL is a value. Null is a value that gets returned often in some functions when that function has failed. So instead of returning an actual string, it just returns a special type of string, which C refers to as null. And the actual contents of that string, it's not like there's any characters in that string. And it actually has something to do with pointers, which we'll cover later in the course. But what you need to understand is that null is reserved for when something fails. You only use null when something fails. And the only reason we check for null in that situation is to make sure that getString didn't fail, that it succeeded. Questions? Anybody?
And why would getString fail if your string is like too long?
If you write a string into the prompt that won't fit in the memory, getString won't be able to allocate enough space for it, so it will freeze up and say, look, there's too many characters here, I'm not going to bother trying, I'll just tell you that it failed.
And is that, so getString was implemented by CS50, so that's just something that they would have put in there?
Yes.
Within that function itself would be something that allows for checking the memory and making sure that there is enough memory for that string.
Yes.
And
So
if there isn't.
when getString is getting a string, it makes sure that there's enough memory, but obviously it doesn't know how much you're going to input.
Yeah.
So it starts by allocating a certain amount of memory. If that's not enough, it goes more and more and more. If it happens to try and allocate more memory than exists in the system, that's when it'll return null and stop trying.
Okay, this might be a bit too thorough, but let's say if I do enter a really big string, if memory is randomly accessed, if it accesses a certain point in memory, that if it's got to represent a sequence of those characters, but that actual selection of memory that it randomly chose does not fit that sequence, or it does fit that sequence of memory, but then it needs more, can it go somewhere else and get some more memory from another random place in memory?
The idea of strings is that the characters are stored next to each other in memory,
So
and that's what allows us.
It's got to find memory that's got that many sequences.
It has to have a contiguous block of memory, because when we do functions like strlen, we have to quickly index the next character, and since the program only keeps track of the first character's location, there's no way for it to keep track of the string pauses here and continues here. So essentially, if you don't have enough, if there's no block of memory big enough for that entire string in the whole system, that's when we'll get a null. Any other questions? Yes.
If the string doesn't fit in a given area, but will the memory move stuff around to try and accommodate it, or will it just say not possible?
I'm not sure that the memory will move around to try and accommodate it. I think it'll try and, when it's allocating memory, it'll try and do it in a smart way so that it minimizes the use of memory. So it's not actually going to randomly throw stuff around. They have a system for where variables get stored in order. So at the time of storing the memory, it'll make sure it optimizes it, but it won't try and, I don't think it'll try and reshuffle the memory to accommodate a string. I don't think getString itself is that advanced.
You know when you write code in the IDE,
Yeah.
and when you declare an int or a float or a bool, it highlights it for you in a specific color. Why is it that when you write string, it doesn't highlight it?
Very good question. Let me show you what he means in case you don't remember. Int is highlighted in blue. String is not highlighted in blue. This is because int is built into C. Int is a library type of the C standard, whereas string is a data type that the CS50 people have implemented. If we, and we've demonstrated this before, but if we remove the CS50 library, strings stop working, because strings themselves don't actually exist in C. And we're going to talk more about how we make strings work if they don't exist. But if we look at the first error here, very first error, use of undeclared identifier string, because string is not part of the standard library. But we are going to look at how CS50 has made strings work and why there's no need for strings to exist in C, but that's going to come a little bit later, and we'll look into that deeper. Any more questions from you guys? Because it's quite a heavy topic. Okay, then I'm done.